Today I'll be taking you through chapter 6.
Hi.
Hi everyone, hi team. Today I'll be doing chapter 6 with you guys, and I'm excited but also nervous. So, the book we'll be using is data structures and algorithms. We're doing chapter 6 stacks, queues, and deckers. For content 6.1 stacks, we're doing the stack, abstract data type, simple array-based stack implementation, reversing data using a stack, matching parentheses, and HTML tags. For 6.2, it's queues, the queue abstract data type, array-based queue implementation. 6.3, double-ended queues. The DAG abstract data type, implementing a DAG with a circular array and DAGs in the Python collections module. Then will be followed by exercises. 6.1, stacks. What is a stack? A stack is a collection of objects that are inserted and removed according to the last in, first out, the LIFO principle. A user may insert objects into a stack at any time, but may only access or remove the most recently inserted object that remains at the so-called top of the stack. Sima, do you mind explaining that? Or does it mean it's the last in, first out principle that needs to be applied at the so-called top of the stack?
You want me to explain the steps procedure?
At the so-called top of the stack.
It is called step on the stack. I'm trying to check the line. Which line I must explain? Oh, it is so-called top of the stack.
Yes, in the
A
brackets.
user may insert object in time, but may only access or remove the most recent remains on top of the stack. I think here they meant, you see, stack last in, first out. It means the one that came last. When you put on the plate, put
Okay.
in your house, the one that came, you put your first plate, second plate, third plate. One that on top is the one that you put when you put it. When you say, it is so-called top, the one on top, the plate, one good.
Okay, I see the last in, first out principle.
Yes.
Can I continue? Sami, are you also on board? Or do you need any clarification? Hello?
Yes, I'm with you.
Okay, can everyone hear me? I'm audible enough.
Yes, yes, you are.
Okay, thanks. The name stack is derived from the metaphor of a stack of plates in a Prince-loaded cafeteria plate dispenser. In this case, the fundamental operations involve the pushing and popping of plates on the stack. When we need a new plate from the dispenser, we pop the top the top of the stack. And when we add a plate, we push. We push it down on the stack to become the new top plate. Perhaps an even more assuming example is Pez candy dispenser, which stores mint candies in a spring-loaded container that pops out the topmost candy in the stack when the top of the dispenser is lifted. See Figure 6.1. Stacks are a fundamental data structure. They are used in many applications, including the following. Example 6.1. The Internet web browser stores the addresses of recently visited sites in a stack. Each time a user visits a new site, the site address is pushed onto the stack of addresses. The browser then allows the user to pop back to a previously visited site using the back button. Is everyone clear on the example explained? Example given.
Yeah, I'm following.
Okay. Is Taro here or no?
Not yet in.
Okay. Example 6.2, the text editors usually provide an undo mechanism that cancels recent editing operations and reverts to former states of a document. This undo operation can be accomplished by keeping text changes in a stack. Okay, guys, here I've given a drawing. I think it's a schematic drawing of a pest dispenser, a physical implementation of the stack ADT. I don't know, maybe anyone has more example to share.
Uh,
Sami,
uh,
Mr.
uh,
Mtunuze, maybe to clarify a bit
no,
on
I'm
the
following. Uh,
given example. Okay, thanks. 6.1.1, the stack abstract data type. Stacks are the simplest of all data structures, yet they are also among the most important. They are used in a host of different applications and is a tool for many more sophisticated data structures and algorithms. Formally, a stack is an abstract data type ADT such that instant S supports the two methods. The S push, okay, Sma, how do you explain it? How do you say it? The S push E or what? Integer E or what? Add element E to the stop tag through
the
top of stack S.
since E is an element, so when you push, use the method push, hitting the element on top
How
of
do you
the
say
stack.
it? Stack element push or what?
The S not push element is I'm not sure. We can try it anyway. Anyhow,
Okay, on to the next one. Thank you so much. S pop um brackets remove and return top element from the stack S. An error occurs if the stack is empty. Why is it empty in this case?
you asking a question? Oh,
Okay, guys, I think I need to make a note. You'll have to excuse me when I let's have a more engaging session as I myself am also learning. I'm not as clued up as Simara here. So can you have an engaging session?
no problem.
Additionally, let us define the following accessor methods for convenience. The stop return a reference to the top element of stack S without removing it. An error occurs if the stack is empty. So, Smang, why is it empty? Or is it given like that? We need to continue from there.
When I say S,
Or we can just put in the element, any element in this case.
remember the S dot is empty is a boolean, so you either give you true or false. So if your element is if your list is empty, it's gonna give you false. If your element is not if your element is empty, it's gonna give you true. If it's not empty, it's gonna give you false. So here you are checking when you're running your program. It's okay, is my element empty? And then reply return true if it's empty. If it's false, if it has an element, then false. I'm not sure if I'm clear.
Okay, no, I'm following. When it's empty, it's false. Then when it's in, when there's an element inside, it's true. No, I get it. Um, Stack is empty. Return true if stack S does not contain elements. len stack. Return the number of elements in stack S. In Python, we implement this with a special method called len. By conversion, we assume that a newly created stack is empty and that there is no priori bound on the capacity of the stack. Elements added to the stack can have arbitrary type. Example 6.3. The following table shows a series of stack operations and their effects on initially empty stack S of integers. S push 5, it's negative or there's no value. Then the stack content is 5. As to give an example, must I take you through?
No, it's fine with me.
Sami? Okay, 6.1.2 simple array based stack implementation. We can implement a stack quite easily by storing its element in a Python list. The list class already supports adding an element to the end with an append method and removing the last element with a pop method. So it is natural to align the top of the stack at the end of the list as shown in figure 6.2. Sure. Guys, I'm trying to read out loud to make sure that I understand what I've just read. We can implement a stack quite easily by storing its element in a Python list. The list class, the list class about ABC is the ABC up until M.
Yes.
The list class already supports adding an element to the end with append method and removing the last element with pop method. Which one is it?
Remember, method pop, it removes the last element, means remove the M. So usually
The KLM. Which are the
the last one is M.
elements?
The last one is M. Remember, it works on the indexes. So from 0, 1, 2, 3, and the last one. So when you use the pop, you must remove the last index, which is M.
Okay, thanks. Figure 6.2 implementing a stack with Python list. Storing the top element in the rightmost cell. Although a programmer could directly use the list class in place of a former stack class, lists also include behaviors. For example, adding or removing elements from arbitrary positions that would break the abstraction that the stack ADT represents. Also, the terminology used by the list class does not precisely align with the traditional nomenclature. Did I say it correctly? For stack ADT. In particular, the distinction between append and push. Instead, we demonstrate how to use a list of internal storage while providing a public interface consistent with the stack. Okay, Smile, please come through again in terms of explaining when they say demonstrate how to use a list for internal storage. Are they talking about the element, um, the the alphabet in the
You see, the list class is normally when, remember when we do a class that was in Python, when we have to create a list, say ABC, the
yes?
list of alphabet is A, B, C, F, G. These are traditional uh, list for creating a Python list. And then there's a little bit different when we create stack, which is a data class, a data structure where we use stack method. We're using a stack method to use the push method, we use the pop-up, we use the one that I mentioned above. So when they say which one we talking when they say we demonstrate how to use a list
When you
for
demonstrate
internal
how to use a list for internal storage.
while providing while providing a public interface consistent with the stack. Remember when you use the non-public, you use underscore, say underscore list. Your list is private, so it's not on public interface. So when you use a public, you just put a list, an alphabet list, and then you assign it to A, B, C, D, E, F, G.
Okay, thanks. Then what is the difference between the how do you see when it's an append or top method?
Sorry?
How do you see when it's an append or top method?
When you use an append, that's why you use a normal list, like the one that we just assigned to alphabet list and then ABCD. Means when we hit an append, you changing the list to adding maybe say append to adding AUM to appending list. And then when you use push, you use using a stack method. It's a structure called stack. When you put on top of any element that you add, the new one.
So when you append, you add.
Yes, when you append, you add.
Okay, thanks. On to the next topic, the adapter pattern. The adapter design pattern applies to any context where we effectively want to modify an existing class so that its method match those of a related but different class or interface. One general way to apply the adapter pattern is to define a new class in such a way that it contains an instance of the existing class as a hidden field and then to implement each method of new class using method of this hidden instance variable. By applying the adapter pattern in this way, we have created a new class that performs some of the same functions as an existing class, but repackaged in a more convenient way. In the context of stack ADT, we can adapt Python's list class using correspondences correspondences shown in table 6.1. This right here. The S push element, then the L append element. S pop, it's false because there's nothing in. Also as the L pop, then the S top. Okay, Lanagu L negative. What does it mean?
Remember when you're using uh, negative one, that's
Yeah.
that negative slicing means you wanna take the last list, the last element in a list, A, B, C, D, F, E, E is the last one. It means it corresponds with a negative one, the last one. So you're checking the last element of the list. In alphabet, you can just say that.
Okay, noted. Implementing a stack using a Python list. We use the adapter design pattern to define an array stack class that uses underlying Python list for storage. We choose the name array stack to emphasize that the underlying storage is inherently array based. One question that remains is that what our code should do if a user calls pop or top when the stack is empty. Our ADT suggests that an error occurs, but we must decide what type of error. When pop is called on an empty Python list, it formally raises an index error, as lists are index-based sequences. That choice does not seem appropriate for a stack, since there is no assumption of indices. Instead, we can define a new exception class that is more appropriate. Code fragment 6.1 defines such an empty class as a trivial subclass of the Python exception class. Here we are shown the class empty exception error attempting to access an element from an empty container. Code fragment 6.1 definition for an empty exception class. The formal definition for an array stack class is given in code fragment 6.2. The constructor establishes the member self underscore data as an initially empty Python list for internal storage. The rest of the public stack behaviors are implemented using the corresponding adaptation that is outlined in table 6.1. Hey guys, you'll have to excuse me. I don't know how to explain this table given here of the array stack class.
It's similar the one that you're explaining above. We're using the method of which means you're adding the list, and then as top print it into len means it's a method of putting the element in the list of us.
So normally with my content, when they didn't put anything, it's still gonna be false.
It means the list is empty. And then we need to edit. So you see in the second line, we're adding push. Right? So we're adding the list, which is we're adding the element. Right? And then just to push. So element first is under, then on top gonna be 3.
Come again?
You see the first line says send to array stack with the empty. We created
Yes.
the list, but it's empty. And then we run the second line, which is s dot push the element 5 inside. So we in the S list, we put in the content 5. It's gonna be 5. Then the third one, say S push 3. So now we're adding the 3 on in the list. So in order to access the list, it means 5 is under, and then on top is 3. And then print into elements into len or len. We're printing the list inside of the S. The output will be 2 because we have only 2 indexes inside. And then print into S top. So we're removing the last list. So we're gonna take out 3. Okay, continue.
So when it's double bracket, the output will definitely be false.
Where it says print into S dot is empty. That one.
Yes.
You see,
Yes.
the method is empty. It's asking us, is our list empty? Remember our list is 5. We got number 5 inside it in the list. So we got a 5 inside. So it's gonna be false because it's not empty. There's a 5 element. There's element 5 inside. It's gonna be false.
Okay, that's noted. Thanks. Okay. 6.1 stacks. Class array stack. I don't know. Should I do this? Should I print? Should I do this on VS Code or what? Guys,
Yes. So
guys,
okay, so yeah, you can code it or you can just pass if you want.
pardon?
Yeah, you can code it. You can code it in on your list on your VS Code.
Or must I continue reading?
Yeah, you can continue if you want to. Just explain what are this, what method for, what blah blah blah. But it's explaining what we just talked about above. And I think we have less than 10 minutes. I'm not sure.
And no, we'll continue up until 2. Analyzing the array-based stack implementation. Table 6.2 shows the running times of our array stack methods. The analysis directly mirrors the analysis of the list class given in section 5.3. The implementations of for top is underscore empty and len use constant time in the worst case. The O element 1 time for push and pop are amortized bounds. Section 5.3.2, a typical call to either of these methods uses constant time, but there is occasionally an O element end negative time worst case, where n is the current number of elements in stack when an operation causes the list to resize its internal array. The space usage for stack O is like, how do you say it? In element n or stack is O element n.
Which line are you reading?
Yeah. When
On,
this I want you to like
on that table, the notice table.
know just how to say it. Do we say the stack is O element n or what?
Oh, the stack is
How
a
to say it?
big O n, which is a linear function, linear time, planning time. A big O of n,
Stack is O.
yes, big O
Okay,
of
come
n.
again.
Stack is big O of n, big O of n.
Okay, thanks. I thought maybe we say element of O. Stack is O element of n. That's the given table, operation and the running time. Stack push E, then O with big element of 1. Am I saying it right?
Yeah, it's fine. You can say big, big O of n, or big O of 1, or big O of, which is a constant sign. And
Table 6.2 performance of our array-based stack implementation. The bounds for push and pop are amortized due to similar bounds for the list class. The space usage is big O, and where n is the current number of elements in the stack. Avoiding amortization by refacing capacity. In some contexts, there may be additional knowledge that suggests a maximum size that a stack will reach. Our implementation of array stack from code fragment 6.2 begins with an empty list and expands as needed. In the analysis of list from section 5.4 4.1, we emphasize that it is more efficient in practice to construct a list with initial length n than it is to start an empty list and append n items even though both approaches run in O number of times. So O is the number of elements, right?
Sorry?
O is the number of elements, right?
O is the
I
measurement
need to check
of
is the number of elements in the deck.
O the measurement of our analysis, our algorithm, how fast it is to how efficient it is. So in a worst case, we use O when if it's linear.
Small, I don't want to continue from there.
Okay, after break.
Pardon?
After because the system's gonna go off now. Okay, after we come.
So when you come back, you want to take over. I don't mind doing the exercise in the VS Code.
Okay, no
I
problem.
think because due to time, so that you don't delay my explanations.
Okay, no problem. Thanks for trying for